talk about mass-independent fractionation because I think it's really, I just want you to be aware of it, have a space in your brain for it. So mass-dependent mass-dependent fractionation, again, mass-dependent fractionation is what you guys have been talking about. So isotope fractionation due to some sort of energy difference accompanying isotope substitutions that are functions of mass, okay? And a general rule is that the energy difference between a substance and its isotopologue increases by the change of mass over m. So this is, the difference, so this is m is your atomic mass of your reference nuclide, and then your delta m would be the difference between this mass and that is the isotope of interest, okay? So these are general, and you guys have talked about it in the beginning of the class. Here again, this slide is not on there. I just wanted to generally, we talk about mass-dependent fractionation, and this is really well described. There's some sort of good layman reviews in Chris and Farquhar of these differences, and just in sort of as normal language as we can fit them in. But there's within the realm of mass-dependent fractionation, it's usually split into equilibrium fractionation and then kinetic processes. Okay. So that's just sort of a general realm. I won't bother to read all of this now. But if you're really interested in these differences, this is on the reference list. This Chris and Farquhar review paper is a very good review paper of this. OK, so the mass independent, or what's usually is now sort of more in favor is non-mass dependent fractionation, is processes that deviate significantly from what you would expect from a mass dependent relationship. Okay, the reason why this NMF is being used more is because there's lots of fractionation processes that might be partially dependent upon mass, right? So they're not fully independent of mass, but there's both mass dependent and mass independent processes going on. So this NMF is a more catch-all term. Okay, so the kinds of effects, and I'm going to gloss over this, but I just want you to sort of be aware of what would cause mass-independent fractionation is a function of electronic nuclear spin coupling effects due to odd mass isotopes that have unpaired nuclear spins. There could be difference in densities of bound states during the transition state chemistry, so resulting from isotopically induced changes in molecular symmetry, which could then affect reaction rates of some different isotopically distributed species. You can have differences in probabilities of conversions between bound electronic states induced by isotope substitutions. And then there's also something that I'll talk about more, is that the photochemistry actually causes different absorption of electromagnetic radiation, which then can result in different isotope effects. Okay, so this is a summary. So symmetry differences, odd mass isotopes, energy states, and photochemistry can cause these mass-independent fractionations. Okay. Why are they used? And how are they used? So has anyone heard of these things? Have used them at all in their research? This is totally new. OK, so origins of the solar system, evolution of Earth and the atmosphere, and the rise of atmospheric oxygen and ozone. I'll just present an example from that. They're used actually in physical chemistry quite a bit. Understanding greenhouse gas sources, past and past abundances, aerosol chemistry and transport, understanding mixing between the stratosphere and oxygen chemistry, the oxygen history of Earth, and specifically Earth's oxidative capacity. And also productivity. They're used for productivity, and I'll sort of explain that in a second. Yeah, did you have a question? Oh. Okay. So this is an example, a relatively straightforward example. So sulfur mass-independent fractionation is used widely in geology, and it's been an exciting sort of, so there's an expected relationship between, this is delta 33s, so this is 33 over 32, and then this is delta 34s, 34 over 32. So sulfur, right, has a sort of a suite of isotopes that are actually relatively abundant. And this cap 33s is a deviation from what you would expect, is sort of a mass-dependent relationship. So this is a mass-dependent fractionation. We're governing this relationship. The 33s should just function be a function of the 34s as a function of 0.515. And this difference is this cap 33s, which is the deviation from expected. Okay, and that's what's called an anomaly. And there's this famous, classic, beautiful study that's been done, and this is this 33s, this cap. So everything, so this is in millions of years ago. So this is the beginning. This is 4 billion years ago. This is like the beginning of Earth. This is today. So what has happened in this cap 33s story here? What's the well, oxygenation, but like just, I can't read oxygenation just from this. Like, so I see, what do I see? I see it's basically 0 up until 2.5 billion, go back in time, and 2.5 billion years ago, whoa, it is not 0 anymore, okay? So if I just interpret this, if you're on the line of 0, if you're 0, that means that all of the fractionation, and this is in different rocks that have been measured. Come on. Oh, no. That's not happy. You can't go backwards. Quit Manage Software Center. That might be helpful. OK, let's see if I can go. So that means that up until, so going back between today and 2.5 billion years, everything just fell on this one line. You go older than 2.5 billion years ago, and things fall off the line. OK? And so that's what this is showing. When we're looking at this capital delta, this is what this is showing, that you're falling off the line. So this idea that basically there are these, you know, the short of it is that there's photodissociation of SO2 and SO that happened because there was low atmospheric O2. There was no ozone. That was basically, there was the reactions, these photochemical reactions that could happen and could drive this mass-independent fractionation before 2.5 billion years ago that couldn't happen after 2.5 billion years ago. And it's interpreted as the rise of atmospheric oxygen. Okay? So these processes are happening all around us, and you know, how we sort of record them is a different question. Okay, so that's sulfur, sort of a quick, I just want to plant that in your brain so you know it as a literate scientist, because it's like, how do we know that when the Earth was oxygenated? Well, that's some of the really great evidence. It's not the only kind of evidence, but that's definitely it's a nice sort of example of mass-independent fractionation. Okay, so in oxygen isotopes, which I'm going to pivot to and talk about for the rest of this class, rest of the lecture, oxygen, this is delta 18O, this is delta 17O, this is a review paper by Mark Tiemens. This is this TFL, this terrestrial fractionation line, which is basically has a slope of 0.5. So here are all these different oxygen species. So this is atmospheric water in this gray ellipse here. Standard mean ocean water is 0, 0. That sort of makes sense. SO4, peroxide, CO2, stratospheric CO2, NO3, ozone in the troposphere, ozone in stratosphere. So all of these things that fall off this line are mass-independent fractionation. Okay, so there are a lot of things in our atmosphere that actually fall off this line, including, so this is bulk earth silicate, and I don't even see atmospheric O2 on here, air O2. But anyway, should be a little bit, maybe it's actually, it's a little bit off, but it maybe not even be off on this scale. Anyway, so what we see here is that the stratosphere and the ozone is actually quite enriched relative to waters, okay? And so generally, people have been thinking that if there's a deviation, if you fall off this line, that it's mass-independent fractionation. Okay. One thing that's really useful, and this is why this can be useful, is just to sort of think about this. Even why do I care about this mass-independent fractionation, even if I don't care about Earth history? I mean, could this be useful to any of you guys? Do any of you think about productivity? No. Okay. Anyway, if there's anything that's useful or anything you guys think about different species or mixing in the atmosphere, and I'll tell you that atmospheric O2 doesn't look like it, but it actually is more negative. It falls off this line. So we basically have a natural tracer here, which is big, especially considering that when I talk about mass-dependent fractionation, we're just within this ellipse. Okay. All these mass-independent fractionations, a lot of them are happening through the Chapman reaction and photolysis of ozone, and there's a series of different reactions in this process. But what I want to just highlight to you is that this reaction so we start with this ozone basically going to O2. Ozone has a high cap17O, which means it has a high anomaly. It falls above the terrestrial fractionation line. It also has a high delta 18O. When you go to O2, formed from that, you actually have a low cap17O. You actually fall below the terrestrial fractionation line. And CO2, that's also formed as part of these sets of reactions, ends up having a high cap17O, and this is in a high delta 18O. And this is going to be an important set of relationships that we'll sort of come back to. But it's these photochemical reactions, and I'm not going to go into the details of them, but that actually are causing these mass-independent fractionations. Okay, so that's sort of the source of them. You'll just have to. And we can kind of see some examples of this. This is when you really are lucky when you can put rocket on your symbol. So this is work by Christy Boring that's been done in terms of the delta 18O versus delta 17O of CO2. And looking at CO2, this is looking at stratospheric tracer, so there's exchange up in the stratosphere of CO2. So tropospheric CO2, which is the CO2 that's closest to us, is right down here, and this is the mass dependent fractionation line. So all of this other CO2 is is above this line. If you also go look in terms of the altitude, and this is CAP 17O, so this is, here they're defining what the deviation is from. The higher you go up in altitude, so this is these rocket samples, the more of the deviation in CAP 17O that you get, okay? And so this idea is that the stratospheric tracer you're seeing in CO2, when you have CO2, what do you imagine CO2 that's tropospheric CO2 to be like? If water is down here and stratospheric CO2 is up here, it's positive, what would tropospheric CO2 be like and why? So any sort of ideas? What's the relationship between, if you put CO2 and sort of immerse it and you have CO2 hovering over water, what's going to happen? It's going to dissolve. It's going to exchange. It's really, so do you remember how delta 18O of how delta 18O of waters was measured? One method. You basically put your water into a little vial, and then you eject a bunch of CO2 and you shake it, and then you sample that CO2 and you measure the 18O of that CO2 for your delta 18O of your water, because CO2 equilibrates with water really quickly, right? Okay, if you have CO2 bathed over a watery planet like ours, right? That CO2 that's in equilibrium with our planet is going to be exchanging with it, and so it's going to be getting. It's the same principle of that old measurement that used to be made before Picars came online, but that basically all the CO2 that's in the troposphere should be pretty much exchanging with that signature. So it should have a CAP 17O of 0, okay? So this is a way in some ways to start to parse out the differences in the mixing between CO2 that's very enriched, that has a high CAP 17O, that's influenced by these mass that's CO3, but CO2 that comes from these sorts of reactions is going to look very different than CO2 that's in equilibrium with water on Earth, okay? So we start there, so in terms of sourcing CO2 and try to understand some dynamics of fluxes of CO2, this is really useful, and this is what Christy Boring's showing, is that CO2, that's tropospheric CO2, that's what's in equilibrium with the water on Earth, that has a mass, that's on the mass-dependent fractionation line, as you would expect. And as you go higher up in these rocket samples, higher up in the altitude, you get more and more of that mass-independent CO2 fraction. Okay, I'm just giving you guys examples of how these kinds of systems can work. The other thing is, remember this scale. This is a CAP 17O scale in per mil. Okay, I am going to be talking to you about CAP 17O in waters of per meg, and the reason why is that that CO2, that's looking at the deviation from this little bubble to that line. All the deviations that we're going to look at later in the talk are just within this gray ellipse, okay? So the questions of scale, and this is why people have known about 17O for a while, but we haven't been able to look within that gray ellipse because it's an issue of precision, okay? So here again, there might be, just to inspire you for other things, there might be questions out there. In theory, you know that there should be interesting variation, but we just can't measure it yet. So it might not be worth it if you can't measure it yet, but analytical, techniques improve, right? And so there might be questions that are worth going after if the analytical instrumentation improves, or if you can be part of that improvement and getting it there. Okay, another way that this is used, so this is the same idea of these photochemical reactions, and I know I'm sort of glossing over the details of them, but this would be we wouldn't get to the end of the talk in the mass-dependent variation. But what we end up with is O2 with a low capital 17O and CO2 with a high capital 17O. And this is really useful because this O2 that's coming in from the stratosphere has low cap 17O. And the O2 that comes from photosynthesis has a cap 17O that is basically, that looks like water of 0, okay? So this is where we start to get into, okay, we now have really distinct isotope compositions of O2 coming from the stratosphere, right? CO2 coming from the stratosphere, and then everything that basically starts to get worked into biology or the hydrosphere gets reset to 0, okay? So now, you can kind of start to, hopefully your mind is churning that this is a function of this, so you can start to get at fluxes, right? And you can start to look at the relative contributions of the ins and the outs of both O2 cycle and also CO2 cycle. Okay. This has been used, I'll show you the first example of how this has been used in an exciting way. The isotope compositions, part of what they're dependent upon is actually the amount of PCO2 in the atmosphere that then controls the fluxes of this whole system. And so the CAP17O of O2, of atmospheric O2, ends up being a function of PCO2, which is very exciting when we're always trying to understand PCO2, especially in a geologic record. And so these are some experiments this is some measurements, but then also some theoretical work that's been done as the CAP17O of O2, this is in per meg, not per mag, but per meg. Now we're in per meg, not per mil. So per meg is a thousandth of a per mil. Okay, so I'll be using that per meg notation a lot, and we'll be going back and forth.